We're going to continue talking about chords, but this time we're talking about the relationship between a chord and a radius. So here I already have my figure kind of drawn out. CB is a chord which intercepts arc CB. Okay, and then I have my radius, which is AD. You should notice that the radius is perpendicular to the chord. Now something special actually happens when a radius is in fact perpendicular to a chord. So let's discover what happens. Let's first look at these minor arcs, and you'll notice that I actually have the minor arcs two different colors. So we have arc BD, which is 55.61 degrees, and arc CD, which is now 55.61. Look at that. Okay, so those arcs are congruent. Now, why do you think that is? Well, it has to do with the fact that that radius is perpendicular to the chord. Okay, and we know that the same thing would happen if we had a diameter here, because a diameter is just 2 times a radius. So if a diameter was perpendicular to a chord, it would also bisect that intercepted arc. But not only does it bisect the intercepted arc, it also is going to bisect this chord. So let's look at what our lengths of our chord segments are. We can see that EC is 3.78, which is congruent to EB at 3.78. Now, someone might say, oh, well, is the radius also bisected? Well, from the looks of it, it doesn't look like it is, but we do want to verify just in case. So the length of AE is 2.59, and the length of ED is 1.99. You can see that definitely doesn't work. Now let me move B and you can see what happens. The relationship between the radius and the chord is that they're still perpendicular. So you can see that as those lengths are changing, my arc measures are still staying the same. They're congruent, my 2 minor arcs, and that chord is still remaining bisected, right? It doesn't matter which one I actually rotate here, but just keep in mind that the radius is perpendicular to the chord. This is actually a theorem in our textbook, which says if a diameter or radius is perpendicular to a chord, then the diameter or radius bisects the chord and its intercepted arc. So let's look at these 2 examples. Is QS a diameter? Well, in the first figure, we see that QS is perpendicular to the chord. In the second figure, QS is perpendicular to the chord, but there is a big difference between them. And what is that difference? Right, in this second one here, we actually have that the chord is being bisected. See, that's being bisected right there, okay? But yet it is not in the first figure. So that is not actually a diameter. That would just be another chord. Now this example is probably one of my favorite applications dealing with circles. Is that, okay, we see in this figure that QJ is the radius and it is perpendicular to the chord, and we're told that the radius is 13 and QL is 5. And we want to find the length of HL and then HK. Okay, well, you already know that when the radius is perpendicular to a chord, the chord is bisected. So if we find HL, we could easily find HK just by doubling it. So QL is 5. Now, the one issue that students usually have with these kind of problems is that they don't recognize where every radius might possibly be. We know that all radii of a circle are congruent. So no matter where we draw a radius, it's still going to be 13. So we have to use that knowledge to our advantage. Okay? Right angles. Think right triangles. We know how important right triangles are going to be. I could actually sketch in a radius, QK. I could sketch in HQ if I'd like. It actually doesn't matter where I sketch in that radius on either side, that is, because we know that the radius will always be 13. Now, you just use the right triangle to help you find that missing value. So if I redraw the right triangle, make it a little bit neater outside of the figure, here's H, L, and Q. All right, we know that HQ is 13 and QL is 5. So what can we apply here? The Pythagorean theorem. So 5 squared plus x squared equals 13 squared. And through the magic Sorry, excuse me. Through the magic power of algebra, x is 12, and 12 is HL. And remember that HK is the whole chord, so we just have to double HL, and we would get HK to be 24. Probably one of my most favorite because it has circles, which I love circles, and it's right triangles, and we all know how much I love right triangles too.